talks, and today right now we're gonna start with Danilo Francati, who's gonna tell us about evolving secret sharing made short. Thank you so much, Danilo, and please take it away.
Thank you for the introduction. Yeah, so I'm gonna present evolving secret sharing made short, and that's a joint work with Daniele Venturi. I'm gonna start from the classical setting, so standard secret sharing. We have a dealer with a secret that wants to distribute a secret among some parties. And so you can run the share algorithm, and then you send the shares to the parties. And each of these shares essentially encodes the secret. And the property that we want is that you can, for example, in threshold secret sharing, if you have enough parties above a certain threshold, we can reconstruct. But if we have some parties below the threshold, the secrets remain secret. So you cannot leak you don't leak any information about the secret. So this is threshold, but in general, we can generalize secret sharing for any access structure. So suppose we encode the access structure using a predicate, and if the predicate evaluates to true, you can reconstruct, otherwise nothing is revealed. So we can generalize the notion of security and correctness according to when you have an arbitrary access structure, in this case, A. When we deal with secret sharing, we want always a property that is called monotonicity that essentially says that if you have a set of parties that is authorized, so allows you to reconstruct, any superset of these parties can reconstruct because it includes a subset that is already authorized. In the evolving setting, though, we have a different scenario. So you don't know the number of parties in advance, and you want to still distribute the shares. Even parties will come later. So suppose in this case, we have one party. And the access structure now, since you have one party, is defined over one party. And in evolving secret sharing, you can compute the first share and give it to the first party. And then when a new party arrives, what it happens is that the access structure may change, so it evolves, because now we have an additional party. And the main property here is that we want to compute the second share, but without interacting with the previous one, because it may be offline. That's the key factor of evolving secret sharing. And you can continue like that. So it was initially defined in the information theoretic setting. And when you deal with the information theoretic case, essentially you have an infinite number of parties that could be also exponential. And still, we have some properties to define when we have evolving secret sharing. So the first two are the one that we talked about before in standard secret sharing. So we have security correctness, and we also have a monotone evolution. So monotone here means that if you take an access structure at timestamp I, and you take the access structure at the next timestamp, you have that all the authorized parties that were in the previous timestamp are also authorized in the future one. And also there are two key properties that we need to keep an eye on, is that when you build evolving secret sharing, you don't know the evolution in advance. And this also implies that you don't know how many parties will arrive, because otherwise the problem is trivial. For example, you can compute the share in advance and keep it locally. And this has a relation with the share size, because since you don't know how many parties will arrive, you need to kind of put some redundant information in the current shares in order to allow reconstruction later. So usually we measure the share size also according to the number of parties that are aligned at the moment. So what we do here, in our work, we extend the notion of evolving secret sharing in the computational case. And why this is interesting, because we can build new evolving access structures. And in case the information theoretic ones were already known, what we want to do is to improve the share size, because we can use computational secure primitives that may allow us to do something better. So in the computational case, the situation is more or less the same as in the information theoretic one, but the key fact is that the parties cannot be exponential, because otherwise you have an exponentially running a dealer. What we have is that the number of parties are bounded by some value n that is polynomial, but you don't know which polynomial. So essentially, you still don't know how many parties will arrive, but you are guaranteed that there's going to be polynomial in the security parameter. And also another important fact when we deal about computational security is that we need a way of representing the access structure efficiently. And if you take a look at the information theoretic case, the way it's represented, the access structure is having a sequence of sets where each set is contained to the other. So this represents an evolution. But the key point here is that it doesn't guarantee you that this evolution is, for example, efficiently computable. Could be like requires like exponential space or exponential time to be computed. So that's why in the computational case, we care about only access structure that can be represented in some model of computation in polynomial by a polynomial computation. So some examples could be a graph, for example, where you have parties that are nodes, and two parties are authorized if there is an edge between them. But also you can do more complex stuff like monotone circuits. So you have that each party is a wire of the circuit, and if the party participates in the reconstruction, you set that wire to 1. So, but now since we care about this efficient representation, we need to spend some time in understanding how the access structure evolves. And so the question is, suppose you have a graph at timestamp 3, then arrive a new party, how the graph is going to change. So can you add a new node? Can you add a new edge? And if you can add a new edge, where? Between two old parties or between one new and one old? So these are natural questions. And the same ones can be extended to the case of circuits, like can you add new wires or can you add new gates? Which gate and after which gate? Like, can I put an AND after an OR or vice versa? So what we do in our work, we identify the properties that allow us to reason how the access structure must evolve. So the first one intuitively is monotonicity. And there is another one that is called rigidity that at very high level is the dual version of monotonicity. And I want to stress that this is not new, was implicitly implied by the information theoretic representation of the access structure. But here we make it more prominent because we want to reason on the natural computation. So rigidity says that if you don't have a CRS and the shares of the all parties remain unchanged during the evolution, then you have this kind of informal theorem that says that if you have a set of parties up to n-1, and this set is unauthorized when the access structure is at timestamp n-1, when the access structure evolves, the same parties are unauthorized. And for same, I mean the parties that are up to n-1. So this may seem like meaningless, but the way that we need to use it is that when the new party arrives, what we have is that the newly inserted authorized set in the evolution must contain the new party, because otherwise you contradict rigidity. And with this in mind, we want to reason on how the access structure evolves. So I'm going to give you two examples. I'm going to show you how to build the evolving secret sharing for Baber-type graphs, but I need to define some kind of preliminaries first. And we're going to talk about projective PRGs first. So a projective PRG is a PRG, but you interact with the PRG using some kind of algorithm. So first you have a setup that generates the master secret key, and essentially the master secret key is the seed. And also you have a key gen algorithm that takes the master secret key and a set T composed of some indexes of the output, and you compute a projective key for that indexes. And then you have two correctness properties. So you have that if you evaluate the PRG using the master secret key, you get the output of the PRG, the complete output. But if you use the projective key, you can compute only the bits corresponding at the indexes T that are contained to the projective key. So you can compute a subset of the output of the PRG. And guess what? So security says that the bits that you cannot compute are pseudo-random, even if I give you the. And another important property for projective PRG to be meaningful is that the projective key must be sublinear in the number of indexes you want to compute, because otherwise the problem is trivial. You simply put the output, the bits you care about in the projective key. And so this notion was proposed by Applebaum et al. To build secret sharing in the computational setting with succinct shares. And we kind of inherit some of the technique they use to build evolving ones. And for this talk, we just are gonna use the construction based on RSA. that has a projective key that doesn't depend at all on the number of indexes you want to encode. So the projective key is polylambda. So depending on how many bits you want you encode, the indexes you encode in the projective key. So given that, we can build evolving secret sharing for buffer-type graphs. And to give you an idea of why rigidity is useful, so essentially rigidity tells you that when a new party arrives, for example, P4, you cannot, when there is this evolution, you cannot add an edge between the old parties. Because if you add edges between the old parties, you make an old unauthorized set authorized, and you have contradictory rigidity. So with this in mind, we can build a scheme. How does it work? This scheme, we have left nodes and right nodes because it's a buffer-type graphs. And we are going to have two projective PRG that we are going to call left and right. So left is associated with the left node and right is associated with the right. Suppose as a first node we get our left node. The dealer is going to do the following. So it's going to compute the output of the projective PRG left. And also it's going to compute a projective key associated to the right PRG, where the indexes that you put during the computation of the key is the ID of your neighbor. In this case, nothing, so you put both. And then you set the share, and the share is going to be the projective key right. And you are going to encrypt the bit, in this case, we assume there is 1 bit, the secret, using the bit at index 1, because it's your ID, but of the output of the PRG left. And that's your share. So it's composed by two parts. So an encryption and the projective key associated with the other PRG. When the right node arrives, you essentially do the same, but we switch right with left. So you compute the output of the PRG right, you compute the projective key according to the PRG left, but now as an index, you put 1 because your neighbor is PRG number 1. And then you take, you compute the share, so you encrypt the secret using your ID, the index associated to your ID, this K2, and you also put the projective key of the PRG left, and you continue like that. So why this works? Essentially because we are kind of using implicit rigidity when you build it, because from the old party, you can always take the encryption of the bit, the encryption of the secret. And from the right party, you can take, that's the only case you care about, because you have that, the new party is going to have the projective key with for the old one, because a new authorized set always contains the new party that arrives. So what you can do, you can compute essentially the bit that you're using, that they used for encrypting the secret, and you can decrypt. And regarding share size, this construction, if you assume RSA, you have a share size that do not depend on the number of parties at all, because it's polylambda, because of the property of the projective PRG we're using. I want to also talk about threshold. This is more interesting because the number of authorized set and unauthorized can be exponential. So in evolving threshold, we have a set of threshold, and the threshold change over time. And we assume for simplicity that in this presentation that the threshold evolves in increased order. So we can define the access structure as follows. So AI is the set of authorized set, and is composed by all the previous authorized set plus all the sets that are at least of cardinality I, the current threshold. And this is an example of the access structure, but I don't want to spend time much on rigidity because it's more convoluted here. But I want just to say that rigidity is the way it's defined, rigidity is guaranteed by the fact that the thresholds are increasing. Evolving threshold, we show a construction based on one-way function. So how does it work? So at very high level, the construction works as follows. So at every timestamp, you do a Shamir secret sharing from scratch. And you evaluate the polynomial on all the IDs of the current parties, but you encrypt the one that are not associated with the new one. And then you give all this information to the new party. So what you do, when you have one party, you take a polynomial F1 at random that encodes the secret, and the threshold is T1 minus 1. And you sample a seed of a PRG, and you give this to the party. But you evaluate the polynomial on the ID1. When the new party arrives, what you do, you sample a new polynomial that encodes the secret, and the threshold changes because that's the way it evolves. You sample a new PRG seed, and also you compute the next unused block of the previous party, output of the PRG. And with that block, you encrypt the evaluation associated with the polynomial evaluation associated with the old one. So you give, in this case, F2 in clear, the PRG seed K2, and then also you evaluate F2 on point 1, but you encrypt it using this PRG block. And you continue doing that. So why it works? Because we have a threshold in this K2, for example. So you can essentially take from the new party the encryptions plus the evaluation of corresponding to this ID 3, and then you use the seed of the previous parties to decrypt the other evaluations, and then you do a Lagrange interpolation and you reconstruct the secret. And regarding the shared size, so these schemes in the computational setting, assuming one-way function, has a shared size that is linear in the number of parties, whereas other information theoretic construction cannot go, at the moment, do not go over n to the 4. Yeah, so there are other results in the paper. I'm going to just mention some of them. So we have other access structures like monotone circuits, CNF, DNF, and also we have a construction for arbitrary access structures, but restricted on only those that has a polynomial number of solutions. And this access structure is interesting because it actually circumvents Mazur information theoretic lower bound for evolving secret sharing. So that supports the fact that it's an interesting setting where to study evolving secret sharing. And also we have another result that we show essentially how to do information dispersal for the evolving case. And we showed that if you know a lower bound on the smallest cardinality of the authorized set of your evolving access structure, you can do information dispersal also in the evolving set. But you can check the paper for these other results. And yeah, that's all. Thank you.
Okay, so we definitely have time for questions in case there is any from the audience. Yeah.
What about verifiable evolution?
Well, we don't study that notion in the paper, but it's natural and there may be an interesting line of future work, but we don't have any result on that.
There was another question around here as well, in the front.
While your work is on computational setting, you continue to use summary secret sharing, but you have, there the share size is same as the secret size, the ideal versions, but you have computational secret sharing, which is where you have the share sizes almost 1/n of the secret. I mean, those construction would apply to your
Can you repeat the
computational secret sharing, where the share size is 1/n fraction of the secret size.
Okay.
I mean, those construction can fit in here because you continue to use information theoretic secret sharing, summary secret sharing, but overall your result is in the computational setting.
Yes.
So what I'm saying is that instead of perfect secret sharing, you have those computational secret sharing, plain threshold computational secret sharing, whether they can be put in as a building block.
They can. I'm not sure you need to open the box to make it work, but the technique may be useful for sure.
More questions? So just a quick one. I don't see a lot of hope for linearity in any of these, right?
Yeah.
Not even the Shamir one, because that one is polynomials here and so on.
Linearity, you mean?
Homomorphic, like that you can.
So one of it really depends on how you define it. So if you want to do linear homomorphic operation between different epochs, it's complicated because the shares have different sides. So you need to have an ad hoc operation. Between same epochs, maybe, but the current construction do not have it.
Well, let's thanks Danilo again. Thank you so much. And then I invite the next speaker to come upstairs, please. Does your mic work?
Hi, everybody. Yes.
Okay, yeah, perfect. So, okay, now to the second talk of the session. Now we have Alireza Kabutsi, who's going to tell us about time secret sharing. Please take it away. Thank you.
Thank you for the introduction. Hi, everybody. I'm Ali Reza. This is a joint work with Aydin and Philip. As the title suggests, we explore the connections between time cryptography and secret sharing. Before I explain why and how, let's just have a quick overview of the basic properties of the tertiary secret sharing, which is the focus of this work. The tertiary secret sharing actually enables the dealer to share a secret towards a set of parties such that any tertiary number of parties can reconstruct the secret. If the dealer is honest, then the reconstructed secret will be the one shared by the dealer. And also the dealer could go offline anytime after the sharing. However, traditionally, there hasn't been any explicit restriction on when to reconstruct the secret. But why this when matters? The first motivation is something about maximal extractable value, which is a serious issue in the context of blockchain and cryptocurrencies, allowing validators, or actually blockchain nodes, to benefit from users by reordering their transactions in a block. A principal countermeasure against this MEV problem is to hide the transaction content until the time that they get committed in a block. So this is usually realized by having each party encrypt their transaction and then secret share the key towards the validator so that the validators commit to the encrypted transactions and then do the reconstruction. However, a natural question that comes up here is that what if the validators collude and do this reconstruction ahead of time? But this question indeed is serious because of three main reasons. The first reason is that the validators essentially benefit from the users as an independent set of parties by doing this collusion. And also this collusion could be unobservable, meaning that the validators could do their job as a consensus node, but behind the scene do this collusion. And also this collusion is essentially an honest majority violation. However, it does not affect the liveness of the protocol because this reconstruction anyway should happen because of that MEV problem that I just mentioned. So this is where imposing a lower time bound for secret reconstruction comes into play, ensuring no party is able to reconstruct the secret before sometime T1. An independent motivation for actually the role of time in the secret sharing is the fact that tertiary secret sharing essentially creates a public goods game dilemma. So this is due to the fact that only a threshold of shares is enough for the reconstruction. So the parties may remain inactive and wait for others to come forward and present their shares. A common technique in the literature to mitigate this issue is to assume an on-chain incentive mechanism so that anybody who presents their shares sooner can get rewarded. So we asked this question, is it possible to have an alternative solution without relying on this on-chain incentive? So this is where imposing an open time bound comes into play. pushing parties to do the reconstruction as soon as possible. So now I'm going to talk about how we realize this lower and upper time bounds for secret reconstruction in a tertiary secret sharing. So we start with the basic tertiary secret sharing scheme, which is Shamir secret sharing. So the dealer constructs the shares, and then he embeds each share into a puzzle using a time block puzzle and send this puzzle privately to each party. So the party starts solving the puzzle until sometime T1 to solve the puzzle and retrieve the share. So this is a very basic scheme for time secret sharing. So for the verifiable setting, the dealer needs to initially convince the parties that they indeed obtain their valid shares after the lower time bound T1. This is important because, of course, the parties should not put time and effort into solving this puzzle without ensuring that they get the valid shares. So in order to do that, we take a VSS protocol, in particular Bellman VSS, which is a principal VSS schemes. And however, we make a crucial change in it. Instead of committing to the coefficient of this degree T polynomial, we commit to the set of shares, GS1, GS2 until GSN. So we do that because this enables us to make use of a primitive called verifiable time commitment. This primitive enables actually committing to some secret value with a discrete logarithm form, as you can see. So essentially, you can think about this commitment to the shares as a set of public keys, where the dealer has committed to their corresponding secret key and has sent the commitment to each party together with the associated validity proof. This is it. However, this is not enough because this only ensures each party that they indeed obtain their shares after sometime T1. But this doesn't mean that this share indeed comes from a degree T polynomial. In order to do that, we actually make use of a linear error correcting code lemma that enables efficiently checking that all of these shares are valid with respect to some degree T polynomial. This is because of the equivalency between Shamir secret sharing and linear error correcting code. So with these two verifications, we can ensure that the protocol works fine. So this is verifiable time secret sharing. For the next variant, we consider publicly verifiable time secret sharing, where not only each participating party, but also anybody should be able to verify the validity of the shares and also the extractability of the puzzles or of the log shares. So in order to do that, we take a PVSS scheme, in particular a scrape PVSS, which is again a principal PVSS scheme in the literature. In the PVSS, by the way, the dealer needs to encrypt the shares under the corresponding public key of the participant, of the parties, and then send a vector of encrypted shares. Here in our protocol, we need to blind these encrypted shares using some blinding value, as you can see, beta I. So we have this CI, S hat I, G3 beta I to blind the encrypted shares. And also, in order to prove that these blinded encrypted shares are well-formed or contain the same share as the committed ones, we use some Sigma protocol. We call it blinded DLEQ, the discrete logarithm equality proof, in order to actually prove this equality. And after we do that, the dealer actually put these blinding values into, again, some time lock puzzle and release the set of all of the puzzles publicly to the parties. So at this point, apart from this validity checking for the sharing, the parties also need to ensure that these puzzles indeed contain valid blinding values so that they can extract their shares after T1. So in order to do that, we use some standard technique, which is actually cut and choose technique, because these time lock puzzles work on group of unknown order. So an efficient solution for this checking is based on cut and choose, where the dealer randomly opens up to T puzzles and to show that all of these ZIs, these puzzle ZIs, indeed contain valid blinding factor. Okay, so we saw how to realize this lower time bound for 3 variants of secret sharing: normal secret sharing, verifiable secret sharing, and publicly verifiable secret sharing. Now we want to talk about how to realize the upper time bound for these variants of secret sharing. Okay, here we start with the publicly verifiable secret sharing that we ended up with for the lower time bound. So the idea, in order to realize this upper time bound, is to relate the correctness of the secret reconstruction to time, meaning that there is no guarantee whatsoever for the correctness if the reconstruction happens after the upper time bound. So if the reconstruction happens after the upper time bound, there is no guarantee that the secret is correct, is the original one shared by the dealer, essentially. So how do we do that? So we again take this PVSS, the scrape PVSS, and so in the scrape PVSS, in the reconstruction phase, each party needs to decrypt their encrypted shares and provide a proof of valid decryption. So what we do here is to piggyback on this proof of valid decryption and make it short-lived. So we have a short-lived validity proof for this proof of decryption. So what is the short-lived proof? Short-lived proof was introduced in Asiacrypt 2022 that are types of proofs with time-sensitive soundness, meaning that their soundness is only guaranteed up to some time, not after than that. So after than that, they could be easily forged. So due to 2 observations, this could result to reconstruction failure. So first of all, these shares have uniform distributions in the scrape PVSS. And also, the short-lived proofs are forgeable after some time and are indistinguishable from the actual proof. So if the reconstruction occurs after the T2, we might end up with some seemingly valid proof together with the garbage shares. And then the reconstruction fails. So this is how we realize this upper time bound for publicly verifiable secret sharing. So for the verifiable time secret sharing, or for the normal secret sharing schemes, we cannot use this trick because there is no proof of decryption in the reconstruction phase. So what we do instead is to relate the security of the secret to time this time. So meaning that there is no security remaining for the secret after the upper time bound, after time T2. How do we do that? So we have this gradual release of additional shares to create some sort of trade-off between time and security. The later the reconstruction starts, the higher chance that the adversary learns the secret even before the honest parties. So, and independently, this technique can provide some form of robustness in the face of dropouts. Particularly, this might occur in some application like secure aggregation in predator learning that they also rely on secret sharing in some sense. Okay, so how we realize this gradual release of additional shares? We again take a VSS or normal Shamir secret sharing protocols, and then we compute these additional shares. These are apart from the usual shares that the parties receive. And then we use this primitive called multi-instance time lock puzzle. This multi-instance time lock puzzle actually contains a batch of messages or batch of shares in this scenario, and only enables solving the puzzles one after the other. So you cannot solve all of the puzzles at the same time. You need to first, in order to solve the next puzzle, you first need to solve the previous puzzle. And also, there is no need for the dealer to stay around. So although this gradual release happens over time at frequent points in time, but the dealer, because of the properties of this multi-instance time lock puzzle, can just create this packed puzzle and then release it at the time of sharing. Okay, so this is a big picture of our protocols and their underlying techniques and primitives. So we have time secret sharing, verifiable time secret sharing, and publicly verifiable time secret sharing. As you can see, there are different ways we can realize this lower time bound T1 and upper time bound T2 using the different variants of time block puzzle and also verifiable time commitment, which actually verifiable time commitment uses some form of time block puzzle as a black box inside it. And also the last picture is about this gradual release of additional shares over time. That's it. Thank you.
Are there questions? Okay, so in the meantime, in case someone wants to ask something, I'm wondering, also related to the question I asked earlier, for example, for the case of the lower bound, while the parties are waiting for this lower bound to be met, they cannot compute on their shares, right? It's not like they can start executing some MPC protocol or something to achieve something in the meantime. They cannot.
No, because of the properties of the time lock puzzle, they ensure that computationally they cannot actually recover these shares before this lower time bound.
Exactly, but is that a good property? Like you may want to prevent reconstruction, but computing privately on them may be actually desirable.
In computing the shares, you mean?
No, I mean, for example, in the case of the MEV example
Yes.
you bring up, I'm not sure I understand the setting correctly, but you may want the parties to be able to perform like MPC computations on their shares, no? Even though they're not reconstructing.
Yeah, we don't want parties to reconstruct the secret before some time.
Yeah, but what if you want them to compute on that secret?
So okay, so so if you do normal secret sharing, then they can compute on the shares and they can compute on the secret. But here, what we want because of that application is to ensure that no matter what, parties cannot use that secret up until sometime in the future, because that time is the time where matters for us to keep the confidentiality of our transaction. So they should not even
Yeah, let me try maybe to rephrase slightly. So imagine a setting where you want the parties to not be able to reconstruct now, maybe tomorrow, but I do want to enable them to compute privately on their shares in your solution if they don't have them yet. So I want them to be able to compute something so that tomorrow they can reconstruct not the original secret, the function of the secret.
That's interesting.
But it's not enabled, right? Because
Yeah.
Is there any question?
This is usually the case, sorry, in the MPC application.
Yeah, that's what I want.
Yeah.
Is there any other question from the audience? Okay, with that, thank you very much again.
Of course.
Please, the next speaker. The next speaker is online. Emanuela, can you hear us? Can you please unmute yourself?
Can you hear me?
Yes, we can hear you. You can hear me, right?
Yeah. So let me share the screen.
Yeah, we can see the Zoom. So if you share your screen, we should be able to go.
Can you see the slides?
Yes, we can see the slides.
Okay.
Yeah, so audio is coming through and we can see the slides, so I think we're ready to go. So right now we have Emanuele Giunta presenting remotely on verifiable secret sharing from symmetric key cryptography with improved optimistic complexity. And thank you very much for attending online, and please take it away.
Okay, so thanks for the introduction and sorry for attending remotely. So this is joint work with Daniel Escudero and Daniel Escudero, and is essentially work on verifiable secret sharing with, okay, as said, improve optimistic complexity. So first of all, let me start by saying what secret sharing is. So a secret sharing scheme essentially is simply a protocol within a dealer and a set of verifiers. The dealer initially holds a secret that wishes to share among these several users. And I mean, essentially the dealer will send to each of these users one share of this secret in such a way that T privacy holds, meaning that, at least in the case of threshold secret sharing, meaning that T parties or less should be unable to learn any information whatsoever about the secret, whereas T+1 party or more should be able to reconstruct the secret initially shared by the dealer. So the easiest example the easiest example of secret sharing and the most used in practice, I would say, is that of Shamir secret sharing, where essentially the secret is a field element, and each verifier is assigned to one point of the field. So initially, the dealer will sample a random polynomial of degree t, so that the evaluation of this polynomial in one given point will match the secret that it's trying to share, and sends to each user the evaluation of this polynomial in the assigned points. So now this has T privacy because less than T party will be unable to interpolate the polynomial, but T+1 parties can interpolate this polynomial and later evaluate this to one point. Now, the only point I want to make about all this discussion is that the only thing you actually need is interpolation and evaluation, which means that Shamir secret sharing is also defined over rings, as long as the points you are using for evaluating are essentially unexceptional sets, meaning that the difference are invertible. And so what I will say in this talk, essentially, we also apply to rings, although I will never mention ring again in the presentation. So one issue about Shamir secret sharing is that, unfortunately, is not binding toward the secret that the dealer is sharing. So one issue, for instance, could be that the dealer could, for instance, send essentially inconsistent share. Think about the dealer sending random points as opposed to evaluation of an actual degree T polynomials. And this means that different reconstructing sets will eventually recover different secrets, and that's an issue for some applications. Or a different attack could be that some verifier could use a different share than the one provided by the dealer, eventually leading to the reconstruction of a different secret. And this is absolutely an issue for applications such as distributed key generation, where you want the secret to be fixed once the dealer has shared it, and to not depend, of course, on the contribution of other parties when you want to jointly compute public and secret keys. So to fix this issue, verifiable secret sharing was introduced, and essentially it consists of two protocols, share and reconstruct. Of course, we still want this to be a secret sharing scheme, meaning that you want to have T privacy, and in particular, of course, T or less parties should be unable to reconstruct any information about the shared secret. But we want to further enforce a new property called commitment, where we say that after the sharing phase is completed, there exists one unique secret that all honest party will reconstruct, no matter what malicious party will do. So this is also considering both corrupted dealer and corrupted verifiers. Strengthening of this property actually enforces that commitment holds, and also that parties get consistent shares that actually reconstruct this secret, but this is just to cover eventually some just corner case, which I won't discuss further in this presentation. Okay, so the setting we investigate essentially is the one with honest majority, so where we have at most half corruptions. And in this setting, we do require synchronous communication, so I will assume synchronous and broadcast throughout the talk. And in this setting, we have essentially three classes of construction. So one essentially is based on essentially achieves statistical security, which is very high security level that we can hope for. But unfortunately, all the construction that we know of involves a quadratic amount of communication among parties. That is unfortunately inefficient in practice if you want to combine or run several instances of the secret sharing scheme. A more efficient class of construction is based on public key assumptions, and the original example is the one of Ferelman, but there are several other constructions. Some achieving even stronger security guarantees. But the issue is that although they only involve a linear amount of communication, they are not post-quantum secure, at least in most cases. And they involve expensive public key encryption operations, such as exponentiations. So in the middle between these two words, we have constructions that are based on secret key encryption or the random oracle, that are possibly post-quantum and also do not involve public key encryption operations. So I will be focusing essentially on this setting, and in particular, the recent construction by Aptor et al. In 2023. So in their construction, essentially, they define a verifiable secret sharing where the dealer complexity, essentially the dealer only has to broadcast a linear amount of information, which is essentially optimal, probably. In the worst case, all the verifier have to download all this broadcast information by the dealer. But the issue we observe is that this actually has to happen even in the best case, where there is no active corruptions. There is no corrupted user actually trying to disrupt the protocol. So no matter what, all the verifier always have to download a linear amount of information and perform a linear amount of hash evaluations. Now, we argue that this is undesirable in some sense because in many protocols, you are more often the verifier than you are the dealer. So improving verifier efforts essentially is useful in gaining amortized complexity. And what we do in our work essentially is try to improve on the verifier complexity in this sense. So we define a new scheme where the dealer complexity is slightly worse. It has to upload more information than in the previous work. But on the other side, in the worst case, we have matching complexity, whereas in the case of few active corruptions, we do have polylogarithmic download size and computational effort. Okay, so let me start by reminding the last year construction, just an overview. So this is essentially just a generalized NOR protocol in some sense. So the dealer starts with one secret S, and it samples two polynomials, one essentially encoding information about the share and one acting as a masking polynomial. It evaluates both these polynomials in all the points assigned to each verifier. So you have a long list of commitments, a linear list of commitments, and each commitment contains the evaluation of F and B in all these points. And to each verifier, it sends the shares, the evaluation of F and B in the point, along with extra opening information I'm not writing in the slides. Now, all the verifiers jointly sample, or at least agree on some random challenges, and this will later actually just be the hash of all the public information. And the dealer later sends the linear combination of B and F. So it's just as you would expect in a Schnorr protocol, Schnorr-like protocol. And next, what the verifier does is that it checks that the share it receives are consistent with the commitment that the dealer broadcasts. And by the way, I'm using like bold font arrows to denote broadcast and not bold arrows to denote private communication. And if anything is, the verifier notices that anything is wrong, so either the openings are incorrect or the polynomial is inconsistent with the share it receives, it broadcasts a complaint bit. And the dealer later broadcast the share of this verifier, so everyone can later check and either slash the dealer or accept the proof. So zooming out, there are essentially three steps going on in this proof. So the first one is we are sending a commitment to F and B that is unfortunately linear in size, and that's the first issue. We have a low degree test for a random linear combination of F and B, and that's also where where the linear complexity unfortunately comes from. And finally, we have a complaining phase that is common to most VSS protocol in 3 rounds at least. Okay, and this is eventually only an issue only in the worst case where many verifier complains. So fixing the first one is very easy. We can simply replace this long list of commitments with a Merkle tree. So the dealer only now broadcasts the root of the Merkle tree and sends to each party both the evaluation of these polynomials and the Merkle tree openings. For the second part, this is actually the most the technical contribution we have. We develop a new distributed proof for checking low degree, for checking low degree. And finally, for the complaining phase, we do use the fact that Merkle tree can be opened in an efficient way when opening to a linear amount of points. Like the naive way would require sending n log n amount of information. But actually, if you're opening simultaneously to a linear amount of points in a Merkle tree, say if you have a linear amount of complaints, there is an easy way to open by simply sending a linear amount of information instead of n log n. So in the rest of this talk, I will just be discussing our new distributed proof for checking low degree of a polynomial. So first, let me briefly define what distributed proofs are. This is a paper by Bonnet et al. In 2019. So the prover, essentially we have prover and verifier as in the interactive proof setting, but now we have many verifiers. Each verifier is holding one piece of the input, and the prover holds the whole input along with some extra witness. And what it wants to show is that the whole input lies in some relation. Now they can engage in several rounds of interactions among the prover and actually even among themselves. And later they can either accept or reject. So correctness states that if the input lies in the relation, then all verifiers should accept. Soundness instead requires that if there is no input that is consistent with the honest verifier share and that lies in the relation, then at least one verifier should reject. Now I should quickly say that actually this is slightly different from the original definition by Bonnet, where they require all the honest verifier to reject. But for our application, this weaker soundness notion is actually sufficient. Okay, so the relation we will be focusing on is the low degree relation. So we want to simply show there is no witness, and we really want to show just that the points that the evaluations all the verifiers have lies in some degree D polynomial, and that's it. The easy way, so just warming up. So the easy way to prove this in a distributed way is as in the Aptor et al. Paper. We can simply have the prover interpolate all these points, and later sense in clear the polynomial interpolating all the points that the verifier holds. Now notice this is at all not zero knowledge, but in this case we're not interested in zero knowledge anyway. And in particular, it is sound because all the verifier can check that this polynomial is consistent with their own share. So as long as D+1 verifiers accept, the proof is sound. The only issue, however, is that, of course, this requires a linear amount of communication in the degree of the polynomial. Now, a smarter way to, or at least a better way, if you want to minimize the verifier communication, or the load complexity is by using instead, for instance, a polynomial commitment. Now, I haven't defined polynomial commitments, but essentially it's a primitive that allows the prover to commit to one polynomial in a succinct way, and later open this polynomial or evaluate this in a given point, and attach to this evaluation a proof that it's also very succinct that this evaluation is correct. Now, if essentially this ensures if strong commitment holds, strong evaluation binding holds, which I'm not defining here anyway, but holds for many commitment that we know of. Of course, the verifier checks that the proof is valid, but there are many issues with known polynomial commitment schemes so far, and those are, for instance, that some of them are not post-quantum, and this is the case for KCG. And for some of them, we do not know yet of any efficient way of evaluating many proofs simultaneously. So this is called multi-point evaluations, and for instance, polynomial commitment based on Frey, as to the best of our knowledge, like we don't know any better way of having the prover compute all this proof in less than quadratic time, which would defeat the purpose of improving verifier efficiency if we have to make the prover so much more inefficient. So our solution eventually is inspired by Frey, but it managed to be in some sense also simpler, leveraging on the fact that we are in the distributed setting, so we can better distribute the verifier effort. So what the prover does again is it starts with one polynomial it interpolates all the points that all the points given to the verifiers. And as in the FFT case, or in many cases you probably have seen before, it splits the polynomial into even and odd powers. And it sends to each verifier privately the evaluation of these two polynomials in the points that were assigned to them. Later, some random challenges is sampled, and the proof reduces to proving that the linear combination of G0 and G1 is a polynomial of low degree, and in particular degree d-half. And of course, this reduction works, and of course, for this step to work, the verifier also has to check that his own share is consistent with the two evaluations that were sent by the prover in the first step. So this is sound, and the reason this is sound is essentially that each verifier is verifying his own, is verifying this equation in his own point, meaning that as long as you have d+1 verifier checking their own point, you're guaranteed that the splitting was performed correctly, and in particular that the original polynomial you started with eventually had the right degree. Okay. So what I described actually it's in the interactive setting, but it's a public coin protocol where I magically said that you sample this challenge mu. So to make it non-interactive, of course, we have a BCS-like compiler where the mu essentially is not sampled with some random coin tossing, but instead it's the hash of public information coming from before. And in particular, our compiler requires that all private key communication the dealer essentially sends to each verifier has to be essentially, okay, so given all the private information and all the broadcasts, the dealer also has to further broadcast a Merkle tree commitment to all these private messages so that every verifier can then extract from this Merkle tree root by hashing it the challenge for the next round. So this is also, so this incurs in a logarithmic factor in the proof size eventually. And finally, yeah, of course, it sends like all the private information and all the Merkle tree path to each verifier. So just to give a visual of, idea of how the whole distributed proof look like. So dealer and prover and verifier initially starts. The prover computes all these Merkle tree, essentially coming from all the logarithmically many rounds he has to do to prove the degree of the initial polynomial is D. So he has many Merkle tree, all for this polynomial G0, G1. It sends to the verifier all the evaluations for each round along with this proof. And notice that, by the way, if you start like with sets of evaluation points that are roots of unity, the size of this Merkle tree halves in size every time, meaning that the prover eventually only performs a linear amount of work only to compute the Merkle trees, and quasi-linear to compute to interpolate all these polynomials. And finally, yeah, and all these proof size essentially are, decreased by 1 at each round. So eventually, the communication size only amounts to log n squares half. So by the way, we're also not hiding any high constant as in the case of Fry or others related proofs. And this eventually completes the distributed proofs in the non-interactive setting. So just to recap, so I showed a new VSS based on previous work in the random oracle model that achieves sublinear download the computational complexity in the best case where there are few active corruptions, but in the worst case still achieves comparable costs compared to previous work. So I would thank you for your attention, and yeah, that would be the end of my talk.
Thank you so much, Manuela. Do we have questions for the speaker? So, Manuela, I think I do have a question for you. You use the random oracle model for the, of course, non-interactive aspect of it. When you instantiate the random oracle with an actual hash function, then you get a loss in security, right? Like in practice, you get a loss in security, and there are papers that study these actual impact in practice for, let's say, Fry. So my concrete question is whether your work could leverage those existing results that study the actual security of Fry to reach some conclusion on the actual security of your scheme.
Okay, thanks for the question. So I'm not entirely aware of studies like addressing the actual security when compiling, when transforming the ROM, essentially this with an hash function. I would say, however, that eventually our security proof is significantly different from the Fry one, especially because at each step of our reductions, so in the case of Fry, you do need rewinding and you do need to know that the set of points, so this is a low degree proximity test, so you need to ensure that your polynomial is not getting too far away at each round every time you fold it. In our case, instead, like all the verifier essentially holds all the information of the polynomial. So in each step, we can always reconstruct what the dealer is sending. So we actually don't need rewinding in our proof. And in particular, we can simply do this run by round soundness argument that it's much simpler and also different from the one in Fry. So I would say probably doesn't apply. Yeah, but I would need to look into it more. I would
But
say.
you have a method to estimate the concrete security of your scheme? This is important from a practical perspective.
We do have in the random oracle model. I'm also not aware of techniques of addressing this, like when compiling, actually instantiating this their own with, for instance, SHA-256.
Okay. Yeah, that's very important.
Yeah. Thanks for the question.
Okay. Are there any questions? There is one over there. If you could bring the microphone, please. It's not working yet. It's still not working.
Okay, yeah. So I have a question. Do you need to assume that you have a certain number of roots of unity for your technique to work?
Thank you for the question. So we need that if you want to have the best possible efficiency where the Merkle tree roots, Merkle tree shrink in size every round. Unfortunately, we don't always have roots of unity. So in the case of rings, we may not have them. So in that case, we have like slightly worse communication, I think. I don't remember. I need to check the paper. But the whole proof works even without roots of unity. And the thing is that instead of splitting into even and odds power of the even and odds power of the polynomial, it just splits into the first d half term and the second d half term. And the proof still goes through, only with slightly worse efficiency parameters. Yeah.
Thanks.
Thanks for the question. Yeah.
Okay. More questions? Okay, so in that case, let's thank Emmanuel again. And also Danilo and Alireza from earlier. And this is the end of the session. Thank you very much. Also the end of today's self-talks.
Bye.